Did you know that while armies clashed on a global scale, another war was being fought? It was a war against time, physics, and the limits of human endurance. Massive cities were built in secret. Harbors were assembled in the sea. Pipelines were laid across oceans and continents. All of this happened in a matter of months, sometimes weeks. These weren't just projects. They were desperate gambles. They were feats of engineering that still boggle the mind. How do you build the world's largest office building in 16 months? How do you create an entire industry for a material that barely exists, hidden from the world? And what happens to the people who are asked to do the impossible? The story of the Second World War isn't just about battles. It's also about blueprints, bulldozers, and impossible deadlines. It's about the colossal things we can build when we have no other choice. Number 17, could you invent a whole new industry in under 3 years? The problem was rubber. In 1941, the United States used more rubber than any other country in the world. It was essential for everything. Tires for trucks and planes, hoses for engines, gaskets for ships, boots for soldiers. And over 90% of the world's natural rubber came from Southeast Asia. When Japanese forces expanded across the region in late 1941 and early 1942, that supply was cut off almost overnight. The American stockpile was small. Experts predicted it would be gone within a year. Without rubber, the Allied war machine would grind to a halt. It was a crisis on a scale that's hard to imagine today. The solution was a massive gamble. The American government decided to create a synthetic rubber industry from scratch. This wasn't a small task. It was like deciding to build the entire modern tech industry in a couple of years. Before the war, synthetic rubber was a niche product. It was expensive and difficult to produce. In 1941, the entire U.S. output was just a few thousand tons. The goal set by the government was to produce over 800,000 tons per year. It seemed impossible. The project was a sprawling nationwide effort. It involved a partnership between the government, oil companies, chemical giants, and universities. The government formed the Rubber Reserve Company to manage the whole thing. They poured over $700 million into the program, a huge sum at the time. This money funded the construction of 51 new factories across the country. These weren't just simple factories. They were complex chemical plants, many built in places like Texas, Louisiana, and Ohio. They had to be built fast, using materials that were already in short supply because of the war. The key players were a mix of scientists and industrialists. People like William Jeffers, the head of the Union Pacific Railroad, was put in charge as the rubber director. He was a tough, no-nonsense manager, not a scientist. His job was to knock heads together and get it done. He famously said, "One thing is certain. We are going to get rubber. We may have a little difficulty with the war, but the rubber is going to be produced." This attitude defined the project. Researchers at companies like Standard Oil, Firestone, and Goodyear worked around the clock to refine the process for making what was called government rubber styrene, or GRS. This became the main type of synthetic rubber used. The sheer speed was incredible. A plant that might take years to design and build in peacetime was being thrown up in months. For example, a massive plant in Port Neches, Texas, went from a blueprint to producing rubber in just over a year. This happened all over the country. By late 1943, the new plants were starting to come online. By 1944, American synthetic rubber production exceeded 700,000 tons. The crisis was over. The Allied armies had the tires and equipment they needed. This massive rushed project is often forgotten, but it was just as important as building planes or ships. Without it, the war could have gone very differently. The effort was documented in government reports at the time, like the Report on the Rubber Program, 1940 to 1945, which laid out the staggering numbers and tight timelines. What secrets about the long-term environmental impact of these hastily built chemical plants remain buried in old company files? How many unrecorded industrial accidents occurred in the rush to produce? And what was the true human cost for the workers? Did the intense collaboration between competing corporations create secret cartels that shaped the post-war chemical industry for decades? Number 16, could you build a city for 40,000 people in just 16 months? Before 1941, the United States War Department was a mess. It was scattered across 17 different buildings in Washington, D.C. Communication was slow. Coordination was a nightmare. As the world edged closer to a global conflict, it became clear this was a serious problem. The military needed a central nervous system, a single headquarters where everyone could work together. The idea for a massive new building was born out of this necessity, but they didn't have years to plan and build it. They needed it now. The man who pushed the project forward was Brigadier General Brehon Somervell. He was the head of the Army's construction division. Somervell was known for getting things done no matter what. In the summer of 1941, he gave the order to design and build a headquarters for 40,000 people. And do it fast. The initial plan was to build it in Washington, D.C., but the chosen site near Arlington National Cemetery caused a public outcry. So they moved it across the Potomac River to a mostly empty, rundown area called Hell's Bottom. The odd, five-sided shape of the plot of land dictated the building's design. Architect George Bergstrom came up with the pentagonal shape to fit the site. That's how the Pentagon got its name and its famous form. Construction began on September 11th, 1941. The timeline was insane. The goal was to have the building ready for its first occupants in less than a year. To make it happen, work went on 24 hours a day, 7 days a week. At its peak, over 15,000 workers were on site. They faced huge challenges. The war created massive shortages of materials, especially steel. So the engineers, led by Captain Clarence Renshaw, made a crucial decision. They would build the Pentagon primarily out of reinforced concrete. They dredged 680,000 tons of sand and gravel from the nearby Potomac River to make the concrete. This decision not only saved precious steel for the war effort, but also sped up construction. The scale of the project is hard to grasp even today. The Pentagon has 6.5 million square feet of office space. That's more than 3 times the floor space of the Empire State Building. It has 17.5 miles of corridors, yet because of its clever design with rings and spokes, it takes no more than 7 minutes to walk between any 2 points in the building. The first employees moved in at the end of April 1942, just 8 months after they broke ground. The entire building was officially completed on January 15th, 1943. The total construction time was about 16 months. A project that should have taken 4 years was done in a fraction of the time. The final cost was around $83 million. The story of its construction is detailed in books like Steve Vogel's The Pentagon: A History. What shortcuts were taken in the electrical and plumbing systems during the rush that required massive, unpublicized repairs in the decades that followed. Were there secret, unmapped levels or tunnels built into the original foundation for continuity of government purposes that remain off the official blueprints? How many workers suffered long-term health problems from working around the clock with materials like asbestos, which were common at the time, but whose dangers weren't fully understood? Number 15, what if you had to build your most advanced factories underground? By 1943, the German war effort was facing a serious problem. Allied bombing raids were becoming more frequent and more destructive. For factories on the surface were easy targets. This was especially true for the factories building the new advanced jet fighters like the Messerschmitt Me 262. These jets were seen as a potential game changer, but you couldn't build them if your factories were being turned into rubble. The solution was a radical and incredibly ambitious move production underground. The plan was to create a network of massive bomb-proof underground factories. This wasn't about digging a few small bunkers. It was about carving out gigantic caverns inside mountains and using existing mines to house entire assembly lines. The project was overseen by Albert Speer's Ministry of Armaments and War Production and managed by organizations like the TOT organization. They identified dozens of potential sites across Germany and occupied territories. The scale was enormous. The plan was to create millions of square feet of underground production space. One of the most famous examples was the Mittelwerk facility, hidden inside a mountain in the Harz Range in central Germany. This was an existing mine for gypsum. Engineers and forced laborers were sent in to expand the tunnels. They created 2 huge parallel tunnels, each over a mile long, connected by dozens of cross tunnels. The result was a massive underground grid. Inside this mountain, they set up the assembly line for the V-2 ballistic missile. Later, parts of it were also used for jet engine production. The conditions were horrific, a detail often separated from the pure engineering challenge. For the Me-262 jet fighter, several underground plants were constructed. A project code named Raymug was built in the Walpersberg Mountain near Kala, Thuringia. Workers blasted out huge galleries and tunnels. They built a concrete runway on top of the mountain. The idea was that finished jets could be brought up to the surface by a massive elevator, take off from the mountaintop, and fly directly into combat. Another complex known as B8 Bergkristall was built near St. Georgen under Gusen in Austria. It was a labyrinth of tunnels designed specifically for Me-262 fuselage production covering around 50,000 square meters. The construction was brutal and incredibly fast. It relied heavily on forced and slave labor from concentration camps. This is the dark side of the engineering achievement. Without this manpower, the projects would have been impossible on the required timeline. Tens of thousands of people worked in terrible conditions using basic tools to dig through solid rock. The projects were a constant race against time. As Allied bombers hit one factory, the pressure to complete the next underground facility increased. By the end of the war, a significant portion of Germany's most critical arms production had been moved or was in the process of being moved underground. Much of what we know comes from post-war Allied intelligence reports, like the U.S. Strategic Bombing Survey, which analyzed the effectiveness of the bombing and the German response. How many of these underground factory complexes were never discovered by the Allies and remain sealed and forgotten today?
What undiscovered prototypes or advanced technologies were meant in these tunnels as of war?
Are there official government records from that era still classified that detail the full extent of the underground network and what was actually built in them? Number 14, why would you build a secret underground city and never use it? In the mountains of Lower Silesia, a region that is now part of Poland, lies one of the biggest mysteries of the Second World War. It's a project known as Ries, which is German for giant. Starting in 1943, the German government began a massive construction project here. The plan was to create a network of 7 enormous underground structures tunneled into the solid rock of the Owl Mountains. It was one of the most secretive and expensive construction projects undertaken by the regime, and to this day, no one is entirely sure what it was for. The scale of Project Ries is staggering. The construction involved blasting and digging miles of tunnels and huge chambers deep inside the mountains. Some of the completed sections are massive, with reinforced concrete walls and ceilings. The tunnels are large enough for trucks to drive through. The total area of the tunnels is estimated to be over 200,000 square feet, though some believe much of the complex remains undiscovered. The work was done by thousands of forced laborers and prisoners of war, many of whom did not survive the brutal conditions. The project was managed by the Todt organization, the civil and military engineering group responsible for many of the Third Reich's biggest construction projects. The official purpose of Project Ries has been lost to history, because the project was never finished and was abandoned as Soviet forces approached in 1945. There are very few surviving documents. This has led to all sorts of theories. One common theory is that it was intended to be a secure underground headquarters for the German leadership, a safe place to retreat from the bombing of Berlin. The size of the complexes and the fact they were being fitted with power, water, and ventilation systems supports this idea. Some of the chambers seem designed to be offices or living quarters. Another theory is that Ries was meant for secret weapons research and production. The secrecy surrounding the project and its location deep in the mountains would have been ideal for developing and building things like the atomic bomb or new types of missiles, far from the eyes of Allied spies and bombers. The proximity to uranium deposits in the nearby Sudeten Mountains has fueled this speculation for years. Books like The Hunt for Zero Point by Nick Cook have explored these fringe ideas, though concrete evidence is lacking. What we do know is that the project consumed immense resources. Huge amounts of concrete, steel, and machinery were transported to this remote area at a time when those materials were desperately needed elsewhere. The construction was rushed and relentless. When the war ended, the complexes were left in various states of completion. Today, parts of the Ries complex, like the tunnels at Lodars and Osauka, are open to tourists. They are cold, damp, and silent reminders of a huge, mysterious undertaking. The sheer effort involved raises more questions than answers. What was the ultimate top secret purpose of Project Reese? And do any classified documents that reveal the plan still exist in Russian or American archives? How much of the tunnel system remains undiscovered, and what might be hidden in sections that were deliberately flooded or blown up by retreating forces? Were any new technologies or weapons actually tested or stored in the completed parts of the complex before it was abandoned? Number 13, how do you make a submarine base indestructible? During the Battle of the Atlantic, German U-boats were a major threat to Allied shipping. These submarines operated from bases on the Atlantic coast of France in places like Lorient, Saint-Nazaire, and Brest. Early in the war, these bases were vulnerable to air attack. An Allied bomber could sink a U-boat in its pen or damage the facilities, taking it out of action. The German command needed a way to protect their most valuable naval assets. The solution was brute force. Build massive, impenetrable concrete submarine pens. These structures were some of the most formidable concrete constructions of the entire war. They weren't just simple shelters, they were gigantic, self-contained naval bases. The construction, largely carried out by the Todt organization, began in 1941 and continued with incredible speed. The main idea was to build a roof so thick that no existing Allied bomb could penetrate it. The roof of the U-boat pen at Saint-Nazaire, for example, was over 26 feet thick in some places. It was made of multiple layers of reinforced concrete with air gaps and other features designed to absorb the impact of a bomb. The scale of these projects was immense. The base at Lorient, the largest, eventually had 3 separate bunkers, known as Karaman I-3 and 3. Together, they could hold over 25 submarines under their protective roofs. The construction required a staggering amount of material. The base at Saint-Nazaire used nearly 600,000 cubic yards of concrete. This material had to be produced and transported on a massive scale, all while the war was raging. Thousands of workers, including many forced laborers, were used to build these pens. They worked around the clock in a race to make the bases operational as quickly as possible. The pens were more than just parking spots for submarines. They were complex industrial facilities. They contained workshops, power generators, ammunition storage, and living quarters for the crews. Submarines could be brought in, repaired, rearmed, and refueled, all under the safety of the concrete canopy. The Allies knew how important these bases were. They launched repeated bombing raids against them, but the pens worked as designed. The bombers could pockmark the surface of the roof, but they couldn't break through. Even the massive tallboy bombs, developed later in the war by the British, had trouble penetrating the thickest roofs. The story of the raids on these pens is well documented in Royal Air Force Bomber Command records. These U-boat pens were a classic example of wartime engineering pushed to the extreme. They were built for one purpose: to withstand anything the enemy could throw at them, and they succeeded. The structures were so massive and so strong that they were impossible to demolish after the war. Many of them are still standing today. The base in Lorient is now a tourist site where you can see the huge concrete structures up close. They are a stark reminder of the incredible effort that went into building them. What was the true failure rate of the concrete mixing and pouring techniques used in the rush to build these pens, and are there hidden structural weaknesses that still exist today? Are there sealed-off sections within the pens that were used for storing secret documents or technology that were never recovered? How many construction workers' deaths went unrecorded, and what is the true human cost buried in the foundations of these concrete monsters? Number 12, could you build a wall across an entire continent? The idea was simple, but the scale was almost beyond imagination. By 1942, the German leadership was worried about an Allied invasion of mainland Europe. They decided to build a massive system of fortifications along the coast, stretching all the way from the border of Spain to the northern tip of Norway. This project became known as the Atlantic Wall. It was not a single continuous wall like in ancient China. Instead, it was a chain of thousands of concrete bunkers, gun emplacements, observation posts, and obstacles. It was one of the largest construction projects of the 20th century. The task of building the wall was given to the Todt organization. They mobilized a huge workforce. At its peak, nearly 500,000 workers were involved. This included German engineers and specialists, but the bulk of the labor was made up of conscripted workers and prisoners of war from all over occupied Europe. The project consumed a colossal amount of resources. It is estimated that over 17 million cubic meters of concrete and 1.2 million tons of steel were used. All this material had to be produced and transported to thousands of construction sites along a 3,000-mile coastline. The construction was rushed and frantic, especially after 1943 when the threat of invasion became more real. The focus was on the areas considered most likely for an invasion, like the Pas-de-Calais region of France. Here, the fortifications were densest. They built huge coastal gun batteries with cannons capable of firing across the English Channel. They poured thousands of concrete bunkers known as pillboxes to house machine guns and anti-tank guns. They flooded low-lying areas and planted millions of mines on the beaches and in the fields beyond. The design of the bunkers was standardized. The Todt organization developed hundreds of different standard designs called Regelbauten. This made construction faster and more efficient. A construction crew at one site would be building the same type of bunker as a crew 1,000 miles away. The plans specified the exact amount of concrete and steel needed and the exact layout. This assembly line approach was key to building the wall so quickly. The person ultimately in charge of inspecting the defenses was Field Marshal Erwin Rommel. When he took over in late 1943, he was not impressed. He felt the wall was too static and pushed to add more obstacles on the beaches themselves, like slanted poles with mines on top known as Rommel's asparagus. Despite the immense effort, the Atlantic Wall was never truly finished. It was strongest in some areas and weak or non-existent in others. When the Allies landed in Normandy on D-Day, June 6, 1944, they had chosen a section that was less heavily fortified than the Pas-de-Calais. Even so, the bunkers and gun positions they faced were formidable obstacles that cost many lives to overcome. The remains of the Atlantic Wall can still be seen all along the coast of Europe today. Crumbling concrete bunkers sit on beaches, a silent legacy of this gigantic rushed construction project. The details are covered in many historical works, including Stephen E. Ambrose's D-Day, How Many Undiscovered Bunkers and Tunnels from the Atlantic Wall Still Exist, Buried Under Sand Dunes or Hidden in Coastal Forests. What secret communication lines or power cables were laid to connect the fortifications that are not on any known map? Were there experimental defensive technologies like acoustic sensors or remote-controlled weapons that were installed in certain sectors but never used? Well, number 11, could you build a port in England and tow it to France? The problem of invading Normandy was not just about getting soldiers onto the beaches, it was about keeping them supplied. An army needs a constant flow of food, fuel, ammunition, and reinforcements. This requires a port. But the major ports in France, like Cherbourg and Le Havre, were heavily defended. The Allies knew it would take weeks or even months to capture one and get it working again, and in those first few weeks, the invasion force would be incredibly vulnerable. They needed a port immediately, but how do you get a port on a hostile shore? The answer was one of the most audacious engineering ideas of the war. If you can't capture a port, build one yourself and bring it with you. This was the idea behind the Mulberry Harbors. The plan was to construct two massive artificial harbors in Britain, tow them in pieces across the English Channel, and assemble them off the coast of Normandy just days after the D-Day landings. It was a project of unbelievable complexity and scale. Many people, including senior military leaders, thought it was impossible. The project was top secret with the code name Mulberry. The design was a massive collaborative effort involving British engineers, scientists, and military planners. The final design had several key components. The outer breakwater was to be made of sunken old ships called gooseberries, and huge hollow concrete caissons called phoenixes. These phoenix caissons were massive, some as big as a 6-story apartment building. They would be towed across the channel and then sunk in a precise line to create a calm harbor. Inside this breakwater, there would be floating piers and roadways, code-named Whales and Beetles, which would connect to the shore. This would allow ships to unload their cargo directly onto trucks, no matter the tide. The construction was a nationwide effort across Britain. It began in 1943 and was a race against the clock. Over 200,000 tons of steel and 1.5 million tons of concrete were used. Thousands of workers at shipyards and construction sites all over the country worked day and night to build the components. The huge Phoenix caissons were built in dry docks and then floated out into rivers and estuaries to be hidden from German reconnaissance planes. The secrecy was intense. Most of the workers had no idea what they were building. They were just told to build strange concrete boxes or sections of floating road. The plan worked. On June 7th, 1944, the day after D-Day, the first ships began their journey across the channel. The flotilla of tugboats pulling the giant pieces of the harbors was a strange sight. Over the next 10 days, the engineers of the Royal Engineers and the U.S. Navy Seabees worked to assemble the two harbors, Mulberry A at Omaha Beach for the Americans and Mulberry B at Gold Beach for the British. For a short time, it was a success. Cargo started flowing onto the beaches, but on June 19th, a massive storm, the worst in 40 years, hit the Normandy coast. Mulberry A was completely destroyed. Mulberry B was badly damaged but was repaired and continued to operate for months. In fact, in the 10 months after D-Day, Port Winston, as it was nicknamed, handled over 2.5 million men and 4 million tons of supplies. It was a critical lifeline for the Allied advance. The story is detailed in books like Guy Hardcup's Codename Mulberry. What happened to the secret test sites where prototypes of the Mulberry components were evaluated, and what environmental secrets do they hold? Were there alternative, even more radical designs for the artificial harbors that were rejected? And do the plans for them still exist in a dusty archive? How many workers were killed or injured in accidents during the secret high-speed construction of the harbor components? Number 10, how do you hide a pipeline? At the bottom of the ocean. Once the Allied armies were ashore in Normandy, they faced another huge logistical problem: fuel. A modern mechanized army runs on gasoline and diesel. The tanks, trucks, and planes of the invasion force would consume millions of gallons every day. Transporting this fuel in slow, vulnerable tankers was a huge risk. A few sunken tankers could cripple the entire advance. The Allies needed a safer, more reliable way to get fuel from Britain to France. The solution was as ingenious as the Mulberry Harbors. It was called Operation Pluto, which stood for Pipeline Under the Ocean. The idea was to lay a series of flexible pipelines across the English Channel. This would create a direct, continuous supply of fuel immune to air attack and bad weather. It was a concept that had never been tried on this scale before. The project was spearheaded by Arthur Hartley, the chief engineer of the Anglo-Iranian Oil Company. He and his team had to solve a series of incredible technical challenges. First, they needed a pipe that was strong enough to withstand the pressure of the ocean and the rough sea bed, but also flexible enough to be coiled onto a giant drum and laid from a ship. They developed two types of pipe. The first was called Heiss, a flexible pipe similar to a submarine telephone cable, but with a hollow core. It was made of lead, steel tape, and armored wire. The second type, called Hamel, was a more rigid but still flexible steel pipe. The real challenge was manufacturing this pipe in the huge quantities needed and doing it in secret. Special factories were set up in the UK. The Heiss pipe was made in long, continuous sections. The Hamel pipe was made by welding 40-foot lengths of steel pipe together into a single, miles-long pipeline. The next problem was how to lay the pipeline. They needed a fleet of specially modified ships. They created huge floating drums like giant spools of thread called conundrums. A conundrum could hold up to 80 miles of pipeline. It would be towed across the channel, slowly unspooling the pipe onto the seabed. The whole operation had to be carefully planned and executed, often at night, to avoid detection. The first pipeline was laid between the Isle of Wight and Cherbourg in August 1944, shortly after the port was captured and cleared of mines. Over the next few months, a total of 17 pipelines were laid across the channel. They connected to a network of camouflaged pumping stations in Britain. These stations were disguised as houses, barns, and even an ice cream shop. On the French side, the pipelines terminated at carefully chosen points and fed into the main Allied fuel supply lines. By the end of the war, the Pluto pipelines were delivering over 1 million gallons of fuel per day. It was a vital contribution to the Allied victory in Europe. It was a project that combined brilliant engineering with incredible secrecy and speed. Official histories, like the History of the Second World War United Kingdom Civil Series, document the technical achievements of Pluto. Were there secret, experimental pipelines made of new materials that were tested and failed, with the wreckage still lying on the channel floor? How many close calls with German patrols or submarines occurred during the laying operations that were never officially reported? What was the true long-term environmental impact of potential leaks from these hastily laid pipelines on the seabed of the English Channel? Number 9, what makes you sink your own ships to build a bridge? In the north of Scotland lies a vast natural harbor called Scapa Flow. For centuries, it has been a major base for the British Royal Navy. During both World Wars, it was the main base for the British Home Fleet. Its location was perfect for controlling the North Sea. But it had a weakness. Scapa Flow is an anchorage surrounded by a ring of islands. There are several entrances or channels between these islands. In 1917, a German submarine managed to slip through one of these channels and sink a British battleship. After that, the Navy sank old ships called block ships in the smaller channels to block them. They thought this made the base secure. They were wrong. On October 14th, 1939, just a few weeks into the Second World War, the German submarine U-47, commanded by Gunther Prien, did the impossible. It navigated through Kirk Sound, one of the eastern channels, squeezing between the sunken block ships at high tide. Once inside the supposedly safe harbor, it torpedoed and sank the British battleship HMS Royal Oak. Over 800 sailors died. It was a huge blow to British morale and a major embarrassment for the Royal Navy. The impregnable fortress had been breached. Something had to be done immediately. Winston Churchill, who was then the First Lord of the Admiralty, visited Scapa Flow shortly after. He ordered the permanent sealing of the eastern channels. The plan was to build a series of solid causeways to connect the islands of Lambholm, Glimpsholm, Bury, and South Ronaldsay to the Orkney mainland. These causeways would permanently block the channels and make the base secure once and for all. They became known as the Churchill Barriers. Construction began in May 1940. It was a massive civil engineering project in a remote and difficult location. The weather in the Orkney Islands is often terrible, with high winds and strong tides. The project was led by the engineering firm Balfour Beatty. They had to build 4 barriers, totaling about 1.5 miles in length. The foundations were made of huge wire cages called gabions filled with rock. These were dropped onto the seabed. On top of this, they poured tens of thousands of concrete blocks, each weighing 5 or 10 tons. The total amount of rock used was over 250,000 tons. The labor force was a major issue. At first, they used British workers, but as the war demanded more manpower elsewhere, the government decided to use Italian prisoners of war. Over 1,300 Italian POWs were brought to camps on the islands of Lamb, Holm, and Bury. Their involvement was controversial, as the Geneva Convention stated that prisoners of war should not be used for war-related work. The British government argued that the barriers were for coastal defense and thus permissible. The Italian prisoners did the hard, physical labor of quarrying rock and filling the gabions. Among them was an artist, Domenico Chiachetti, who led the effort to build the beautiful Italian chapel on Lambholm, which is still a major tourist attraction today. The barriers were completed in September 1944 and officially opened in May 1945, just after the war in Europe ended. What unrecorded engineering challenges and failures occurred during the construction in the harsh Orkney weather? Are there still undiscovered wrecks or military debris on the seabed near the barriers from the construction process or earlier block ships? What were the real uncensored stories of the relationships between the Italian prisoners and the local Orkney population? Number 8, could you build a highway through a frozen wilderness in 8 months? In early 1942, the situation was grim for the United States. After the attack on Pearl Harbor, Japanese forces were advancing across the Pacific. They had bombed Dutch Harbor in Alaska and occupied 2 of the Aleutian Islands. Suddenly, Alaska, which had seemed so remote, felt like it was on the front line. There was a real fear of a full-scale Japanese invasion of Alaska and then the North American mainland. The problem was that Alaska was almost completely cut off. There was no land route connecting it to the rest of the United States. Supplies and troops had to be sent by sea, where they were vulnerable to submarine attack. The solution was to build a road. A very long road. The plan was to construct a highway through the vast, frozen wilderness of northern Canada and Alaska. It would connect Dawson Creek in British Columbia with Delta Junction in Alaska, a distance of over 1,500 miles. The project was called the Alaska Highway, or the Alcan Highway. It was an engineering task of epic proportions, and it had to be done at impossible speed. The decision to build was made in February 1942. The road had to be passable for military traffic by the end of the year. That gave them about 8 months. The U.S. Army Corps of Engineers was put in charge. They sent over 11,000 soldiers to the north. They were joined by thousands of civilian workers. The challenge they faced was immense. This was some of the most difficult terrain on Earth. There were vast forests, hundreds of rivers to cross, deep muskeg swamps, and mountain ranges. And for much of the time, they were working in extreme cold. The soldiers were mostly from the southern United States and had no experience with these kinds of conditions. A significant portion of the engineering regiments were African American soldiers who worked under segregated and often worse conditions than their white counterparts. Their contribution was crucial, but often overlooked in early histories of the project. The construction method was a brute force approach. They started from both ends and a point in the middle at Whitehorse. Crews would push forward, clearing a path through the forest with bulldozers. They worked 24 hours a day, using headlights at night. They built temporary pontoon bridges to cross rivers, which would be replaced with permanent structures later. One of the biggest challenges was the permafrost, the permanently frozen ground. If they scraped away the top layer of vegetation, the permafrost would melt, turning the ground into a bottomless swamp. They had to build the road on top of the existing ground cover to keep the permafrost frozen and stable. Against all odds, they did it. The two main construction crews, one pushing north and the other south, met on September 24th, 1942, at a place that was nicknamed Contact Creek. A rough pioneer road was now complete. The official opening ceremony was held on November 20th, 1942. In just over 8 months, they had built a highway through a wilderness that people had said was impassable. It was an incredible achievement. The story of the men who built it is told in books like The Milepost, the annual guide to the highway, and more historical accounts like Ken Coates's The Alaska Highway in World War II. The highway secured the supply line to Alaska and remains a critical piece of infrastructure to this day. How many pieces of abandoned, heavy equipment from 1942 still lie undiscovered in the remote Canadian wilderness just off the highway's path? What undocumented grave sites of workers who died from accidents or exposure exist along the original route? Were there secret military installations or airfields built alongside the highway that were decommissioned and erased from official maps after the war? Number 7, how do you get an oil field from Texas to New York overnight? In 1942, the east coast of the United States was facing a severe oil shortage. The problem wasn't a lack of oil. The huge oil fields of Texas were producing plenty. The problem was getting it to the refineries and cities of the Northeast. Before the war, most of this oil was transported by sea in tanker ships that sailed from the Gulf of Mexico up the Atlantic coast. But German U-boats were now prowling the Atlantic. They were sinking tankers at an alarming rate. This Battle of the Atlantic was creating a crisis. Homes were going cold, factories were at risk of shutting down, the military needed a secure way to move oil. The solution was one of the most ambitious pipeline projects in history. The plan was to build 2 massive pipelines, the largest ever constructed, to carry crude oil and refined products directly from Texas to the East Coast. They were called the Big Inch and the Little Big Inch. The Big Inch was a 24-inch diameter pipe for crude oil. The Little Big Inch was a 20-inch pipe for products like gasoline and heating oil. Together, they would stretch over 1,200 miles, crossing mountains, rivers, and forests. And they had to be built with incredible speed. The project was authorized in June 1942. A new government corporation, War Emergency Pipelines, Inc., was created to manage the construction. It was a collaboration between the government and the biggest oil companies. The challenges were enormous. First, they had to produce over 1,200 miles of large diameter steel pipe at a time when steel was being rationed for ships, tanks, and guns. Special permission was granted to get the steel needed. Then they had to dig a trench over 1,200 miles long and lay the pipe in it. The construction was a marvel of organization and hard work. At its peak, over 16,000 people were working on the pipeline. They used the newest and biggest construction equipment available. Teams of workers specialized in different tasks. One team would clear the right of way, another would dig the trench. Then came the teams to lay the pipe, weld the sections together, and wrap the pipe to protect it from corrosion. They worked in all kinds of weather, through swamps in the south and the rocky terrain of the Appalachian Mountains. They had to cross 30 major rivers and hundreds of smaller streams. For the Mississippi River crossing, they had to dredge a deep trench in the riverbed and lay the pipe under the water. The speed was unbelievable. On average, they were laying several miles of pipe every single day. The Big Inch pipeline was completed from Texas to Illinois in just 350 days. The full line to the East Coast was finished shortly after. The Little Big Inch followed. By the end of the war, the two pipelines had delivered over 500 million barrels of oil to the Northeast. They were a crucial lifeline that fueled the war effort and kept the home front running. The project's director, Bert Hull, was known for his relentless drive to get the job done. The story is detailed in publications like The Big Inch and Little Big Inch Pipelines, the most amazing government industry cooperation ever achieved. After the war, the pipelines were sold and converted to transport natural gas, which they still do today. What geological or archaeological sites of importance were destroyed and covered up by the trench digging crews in their rush to complete the lines? How many unrecorded spills and leaks occurred during the initial high-pressure testing of the pipelines that were never made public? Do secret spur lines exist, built for military purposes to supply hidden bases that branch off the main pipelines and are not on any public map? Number 6. Could you build a factory that produced a bomber every hour? In 1940, President Franklin D. Roosevelt gave a famous speech in which he called for the United States to become the arsenal of democracy. He challenged the nation to produce 50,000 airplanes a year. At the time, this number seemed impossible. One of the people who took this challenge seriously was Charles Sorensen, the production chief at the Ford Motor Company. Ford knew how to build cars on a massive assembly line. Sorensen believed he could apply the same principles to building airplanes. Specifically, the huge B-24 Liberator bomber. The result was the Willow Run Bomber Plant, built near Ypsilanti, Michigan. It was the largest and most ambitious manufacturing project of the war. This wasn't just a factory, it was a city dedicated to building one thing. The main assembly building, designed by the famous industrial architect Albert Kahn, was half a mile long and a quarter of a mile wide. It was the largest factory under one roof in the world. It had its own airport with multiple runways, a power station, and housing for thousands of workers. The scale was meant to be overwhelming. Construction began in the spring of 1941, even before the United States entered the war. The land was cleared, and the massive steel frame of the building began to rise. The project was rushed from the start. They poured concrete around the clock. The factory was built and equipped in about 18 months. The goal was simple and audacious: to produce one B-24 bomber every hour. This had never been done before. Airplanes were traditionally built in one place by skilled craftsmen. Ford's idea was to break down the complex process of building a bomber into thousands of simple, repeatable steps. The parts would move down a massive assembly line, just like a car. The beginning was rough. The first B-24 rolled off the line in September 1942. But production was slow. There were problems with getting parts, training workers, and managing the incredibly complex process. The factory was so big that it was hard to manage. It was nicknamed Will It Run because of the early difficulties. But Sorensen and his team were relentless. They solved the problems one by one. They brought in tens of thousands of workers from all over the country, including a large number of women who became known as Rosie the Riveters. A new community with dormitories and apartments was built to house them. By 1944, Willow Run had hit its stride. The assembly line was moving. The factory was churning out bombers at an incredible rate. At its peak in 1944, Willow Run was producing a new B-24 every 63 minutes. It produced over 8,600 bombers in total, more than any other factory. It was the ultimate symbol of American industrial power. The story of Willow Run is a classic tale of wartime production, covered in books like The Arsenal of Democracy by A.J. Bymey. The factory proved that the principles of mass production could be applied to even the most complex machines of war. What experimental manufacturing techniques were tried and failed at Willow Run, and what dangerous shortcuts were taken with worker safety to meet production quotas. Are there sealed archives from the Ford Motor Company that detail the true extent of labor disputes and social unrest among the hastily assembled workforce? What happened to the secret design modifications and experimental B-24 variants that were prototyped at the plant but never went into full production? Number 5, how did one man in New Orleans win a war in Europe? When people think about the iconic equipment of the Second World War, they often think of tanks, planes, and battleships. But one of the most important pieces of equipment was a small, simple-looking boat. It was the Landing Craft Vehicle Personnel, or CVP. This was the boat that carried soldiers from the big transport ships to the beaches in invasions from North Africa to Normandy. The man who designed and, more importantly, mass-produced this boat was a stubborn, innovative boat builder from New Orleans named Andrew Jackson Higgins. Before the war, Higgins built specialized boats for trappers and oil drillers working in the swamps and bayous of Louisiana. His boats had a special design. They had a flat bottom and a protected propeller, which allowed them to run in very shallow water without getting stuck. And they had a ramp at the front, so you could run them right up onto a riverbank to unload equipment. The U.S. Marine Corps saw the potential of these boats for amphibious landings. They were looking for a better way to get troops onto a beach. The Higgins boat was perfect. When the war started, the demand for these boats exploded. The military needed thousands of them, and they needed them fast. Andrew Higgins ramped up production at an incredible rate. His company, Higgins Industries, grew almost overnight from a small local business to a massive industrial enterprise. He built new factories in New Orleans. He hired tens of thousands of workers. He created an integrated production system where his company did everything from processing the lumber to building the engines. At its peak, Higgins Industries employed over 25,000 people, a diverse workforce of men and women, black and white, working together. Higgins used mass production techniques similar to the auto industry. He set up multiple assembly lines. The boats were built in sections and then put together. This made the process fast and efficient. He was known as a demanding boss, but he also inspired great loyalty. He was constantly on the factory floor, solving problems and pushing his workers. The result was a flood of landing craft. Higgins Industries built over 20,000 boats during the war, including the famous LCVPs. These boats were simple, made mostly of plywood and powered by a standard truck engine. But they were exactly what the military needed. The impact of the Higgins boat was immense. Dwight D. Eisenhower, the Supreme Allied Commander in Europe, famously said, "Andrew Higgins is the man who won the war for us." He argued that without the LCVPs, the entire strategy of amphibious assault would not have been possible. They couldn't have landed on the beaches of Normandy. The boat's design, with its front ramp, allowed troops and small vehicles to get onto the shore quickly. It was a simple solution to a complex problem, and it was the mass production of this simple solution that made the difference. The story of Higgins and his boats is a key part of the history of wartime logistics, chronicled in books like Andrew Jackson Higgins and the Boats That Won World War II by Jerry E. Strahan. What happened to the thousands of design blueprints for experimental boat types that Higgins developed, but that the military never ordered? How many unrecorded industrial accidents occurred in his rapidly expanding factories where safety regulations were often ignored in the name of speed? Are there secret company records detailing Higgins's fierce battles with government bureaucracy and rival manufacturers to keep his production lines running? Number 4, can you build a ship a day? In 1941, the Battle of the Atlantic was at its height. German U-boats were sinking Allied merchant ships faster than they could be replaced. Great Britain, an island nation, depended on these ships for its survival. They brought food, raw materials, and military supplies from the United States and elsewhere. If this lifeline was cut, Britain would be forced to surrender. The United States, even before it officially entered the war, realized it had to solve this problem. The answer was not just to fight the U-boats, but to outbuild them. They needed to build cargo ships so fast that it wouldn't matter how many the U-boats sank. The man who stepped up to this challenge was an industrialist named Henry J. Kaiser. Kaiser was not a traditional shipbuilder. He had built his reputation on massive construction projects like the Hoover Dam. He knew how to organize huge projects and get them done quickly. He applied his construction experience to shipbuilding. He decided to build a new type of cargo ship, a simple, no-frills vessel that could be built quickly and cheaply. It was called the Liberty ship. The design was based on an older British design, but it was modified for mass production. Kaiser's genius was in revolutionizing the way ships were built. Traditionally, a ship was built from the keel up in a single shipyard. It was a slow, craft-based process. Kaiser broke it down into an assembly line. He built new shipyards on the West Coast in places like Richmond, California, and Portland, Oregon. These were not traditional shipyards. They were assembly plants. Huge sections of the ship, like the bow or the deck house, were built in factories all over the country. These sections were then transported to the shipyard and welded together. This process of prefabrication and welding, instead of riveting, was the key to the incredible speed. The results were astonishing. The first Liberty ships took over 200 days to build, but as the workers and managers got better at the process, the time dropped dramatically. They created a competition between the different shipyards to see who could build a ship the fastest. In November 1942, a shipyard in Richmond, led by Kaiser, built a Liberty ship, the SS Robert E. Peary, in just 4 days and 15 hours from the time the keel was laid to the time it was launched. It was a publicity stunt, but it showed what was possible. On average, a Liberty ship was being built in about 42 days. At the peak of production, American shipyards were launching 3 Liberty ships every single day. Over the course of the war, a total of 2,710 Liberty ships were built. They formed the backbone of the Allied merchant marine. They were slow and not very pretty, and they had a reputation for cracking in cold seas, but they did the job. They carried millions of tons of cargo across the oceans. They were built by a new workforce, which included many women who had never worked in heavy industry before. The story of Kaiser and the Liberty ships, as told in books like Freedom's Forge by Arthur Herman, is one of the most incredible production stories of the war. It was a victory of mass production over naval warfare. What shortcuts in welding techniques and materials testing were taken that led to the later problems of Liberty ships cracking in half, and were these risks known at the time? How many secret reports on sabotage and labor unrest in the Kaiser shipyards were suppressed to maintain public morale? What happened to the innovative but ultimately rejected ship designs that were proposed as alternatives to the Liberty ship? Number 3, could you turn the English countryside into a launch pad for Armageddon? During the early years of the war, the British Royal Air Force fought back against Germany from its established airfields in the south and east of England. But when the United States entered the war, the entire strategy changed. The plan was to launch a massive combined bomber offensive against Germany, flying daylight raids with the American 8th Air Force and night raids with the RAF. This required a huge number of airplanes, and all those airplanes needed somewhere to take off and land. The England, a small and crowded island, had to be turned into a giant, unsinkable aircraft carrier. The project to build hundreds of new airfields was one of the biggest construction efforts ever undertaken in Britain. It began in 1942 and continued at a frantic pace for the next 2 years. The program was a joint effort between the British Air Ministry and the U.S. Army Corps of Engineers. The standard design for a heavy bomber airfield was a massive undertaking. It required 3 long concrete runways, miles of taxiways, dozens of hard stands for parking the bombers, hangars for maintenance, and barracks and facilities for thousands of airmen and ground crew. The scale of the construction was staggering. At its peak, over 60,000 workers were employed building airfields. They moved millions of tons of earth and poured millions of tons of concrete. They laid hundreds of miles of pipes for water and sewers and thousands of miles of electrical cables. And they did this all over the English countryside in places like East Anglia, which became known as Little America because of the number of American bases there. The landscape was transformed. Quiet villages suddenly found themselves next to a huge, noisy airfield operating 24 hours a day. The speed of construction was critical. A new airfield had to be built in about 6 months. To achieve this, the engineers used new, heavy earth-moving equipment, much of it shipped over from the United States. They worked through all kinds of weather. The process was standardized to make it as fast as possible. Once a site was chosen, teams would come in to clear and level the land. Then came the concrete pourers and then the crews to build the Nissen huts and other buildings. This massive program is detailed in the official histories of the U.S. Army Air Forces and in books like Roger A. Freeman's The Mighty Eighth. By 1944, there were hundreds of airfields packed into the east and south of England. It was the most concentrated collection of air power the world had ever seen. On any given day, over 1,000 bombers might take off from these fields to fly missions over Europe. This invasion by air would not have been possible without the incredible rushed construction effort that turned a peaceful landscape into a massive military base. Many of these airfields were abandoned after the war, and their crumbling runways and buildings can still be found in the English countryside today, a quiet reminder of a time when the sky was filled with the sound of bombers. What was the true extent of the environmental damage caused by the rapid construction, including polluted water sources and destroyed natural habitats? That was never documented. How many undiscovered, unexploded bombs or ammunition dumps are still buried on the sites of these hastily built airfields? Were there secret airfields built for intelligence or special operations purposes that were never part of the official program and whose existence is still classified? Number two, what if you had to build a city just to destroy a city? The most secret project of the Second World War was the effort to build the atomic bomb. It was called the Manhattan Project. But it wasn't just a research project, it was a colossal industrial and construction enterprise, larger than the entire American auto industry at the time. To build the bomb, they first had to produce the fissile materials, either enriched uranium or plutonium. And to do that, they had to build entire cities from scratch, in total secrecy. The three main sites of the Manhattan Project were Oak Ridge, Tennessee, Hanford, Washington, and Los Alamos, New Mexico. Each had a specific purpose, and each was a massive rushed construction project. The entire project was under the command of General Leslie Groves of the U.S. Army Corps of Engineers. Groves was an expert in large-scale construction, having just finished building the Pentagon. He was the perfect man for a job that required incredible speed and organization. Oak Ridge was built to enrich uranium. In 1942, the government acquired a 60,000-acre tract of land in the hills of Tennessee. In a little over 2 years, they built a city of 75,000 people where there had been nothing but farms. The workers who came to Oak Ridge had no idea what they were working on. They were just told it was important for the war. They built and operated two gigantic factories. One called K-25 was the largest building in the world at the time, a U-shaped structure half a mile long. It used a process called gaseous diffusion. The other plant, Y-12, used a different process with huge electromagnets called calutrons to separate the uranium isotopes. The construction was nonstop. Hanford, in the desert of eastern Washington state, was built to produce plutonium. Here, the government acquired an even larger area, half the size of Rhode Island. They built a massive complex that included the world's first full-scale nuclear reactors. These reactors would irradiate uranium fuel rods, and then huge, remote-controlled chemical plants would extract the tiny amounts of plutonium created. The construction of the B reactor, the first one, was a race against time. It was completed in just 13 months. A city was built to house the 50,000 workers. Like at Oak Ridge, everything was shrouded in secrecy. Los Alamos was the scientific heart of the project. It was built on a remote mesa in New Mexico. This is where the top scientists, led by J. Robert Oppenheimer, worked to design and build the actual bomb. When Oppenheimer first saw the site, it was just a small ranch school. Within 2 years, it was a thriving secret town of several thousand people with laboratories, workshops, and housing, all surrounded by a fence. The construction was rapid and often chaotic, as the scientists constantly needed new buildings and equipment for their experiments. The Manhattan Project was a gamble on a scale that is hard to comprehend. It cost nearly $2 billion, a huge sum in the 1940s. It employed hundreds of thousands of people, and it was all done in about 3 years, in a desperate race. The story is told in many books, most notably Richard Rhodes's Pulitzer Prize-winning The Making of the Atomic Bomb. The success of this massive secret construction project changed the world forever. What long-term health studies on the residents of communities downwind from Hanford and Oak Ridge were suppressed by the government? How many experimental reactor or enrichment designs were built and tested at secret, smaller sites that are still not publicly known? Do any of Oppenheimer's personal, uncensored notes still exist that detail his private fears and moral doubts about the construction and use of the weapon he was building. Number one, what do all these projects tell us about ourselves? Looking back at these 17 gigantic projects, a single theme emerges. It is the theme of possibility. In a time of extreme crisis, societies discovered they could do things that seemed impossible just a few years before. They could build cities in months, highways in a winter, and industries from scratch. The normal rules of economics, bureaucracy, and time were suspended. The only thing that mattered was getting it done. This was a war fought not just by soldiers, but by engineers, construction workers, and factory laborers. These projects were driven by fear, but they were built with ingenuity. They showcased the power of mass production organization and single-minded focus. A leader like Henry J. Kaiser or Leslie Groves could mobilize immense resources and manpower to achieve a specific goal. They used standardized designs, prefabrication, and round-the-clock work, shifts to compress timelines that seemed impossible. The results were often not pretty. The Liberty ships were basic. The Willow Run factory had a difficult start. But they worked. They delivered what was needed when it was needed most. The human cost was often immense. The workers on these projects faced dangerous conditions, long hours, and immense pressure. The secrecy of projects like the Manhattan Project or the underground German factories meant that workers had no idea what they were building or the risks they might be facing. The reliance on forced and prison labor in some of the German projects adds a dark and complex layer to the story of their engineering achievements. The history of these constructions is not just a story of concrete and steel, but of human sweat, sacrifice, and sometimes exploitation. The legacy of these projects is all around us. The Pentagon is still the heart of the U.S. military. The Alaska Highway is a vital transportation link. The synthetic rubber industry, born in the war, became the foundation of the modern plastics and chemical industries. The nuclear technology developed in secret cities has shaped global politics for over 75 years. These projects didn't just help win a war, they reshaped the post-war world. They created new technologies, new industries, and new centers of population. They showed what a nation state is capable of when it directs all its energy toward a single purpose. They also leave us with difficult questions. The speed of construction often meant cutting corners on safety and environmental protection. The long-term consequences of these decisions are still being dealt with today. The immense power that these projects gave to governments and large corporations set a precedent for the military-industrial complexes that would dominate the post-war era. The story of these 17 projects is a story of human achievement on an epic scale, but it is also a cautionary tale about the costs of that achievement and the immense power that crisis can unleash. What fundamental human capacity for rapid, large-scale cooperation do we ignore in peacetime, and what would it take to unlock it for challenges like climate change or disease? If society could mobilize on this scale once, what are the real, unstated barriers preventing us from doing so again for positive ends? In the final, desperate days of the war, what miracle projects were started but never finished, their plans and foundations now lost to time, representing a technological path not taken?